I have the pleasure to chair this morning, and with us it's Karol Łukanowski, who will talk about his recent archive that he has put on with Marcin Jarzyna, both working in our center QOT in Warsaw, and he'll talk about capacity of lossy photon channel. The floor is yours, Karol, please.
Thank you very much for this introduction. I hope you can hear me well. So indeed, today I will be talking about the capacity of a lossy photon channel with direct detection. But before I get to this specific topic, I would like to address it from a bit broader perspective, which is the concept of communication. And I guess one could argue that communication of information is, well, really important for the human race, mainly because it allows for the exchange of ideas, and this in turn results in cooperation. And that is crucial for any achievement and progress. And in fact, if one looks around, one can see examples of communication in practically every aspect of our lives. So there is the obvious example of just talking to somebody else, either in person or by phone. But one can cite even some weirder examples, like, for example, DNA can be thought of as communication from the genome to each particular cell, in which the information about what proteins should be produced is encoded. And of course, there is also the big example of practically the whole modern technology, which is based on efficient communication of information. So we have GPS, communication between satellites, or, well, the internet itself. An important thing to also note is that all of these examples are examples of noisy communication. So there's always the possibility of some errors occurring in the communication channels, like, for example, some mutation in the DNA, or if I'm talking to somebody else, I might lose signal and not hear them that well. But nevertheless, I give these examples to kind of make a pitch for information theory, which allows us to analyze them and to ask some important questions. So information theory gives a mathematical model where we are able to ask about how to efficiently encode information and send it, even in the presence of errors, and also how fast can we do it. So this model is can be presented as follows. So we say that typically there is some sender of information, some receiver of information, and between those two persons there exists some channel. And the sender has at their disposal some set of symbols which can be inputted into this channel. And to give a concrete example, this channel, for example, can be an electrical cable, and then those symbols may correspond to some specific electrical signals which will travel through this cable. The receiver of information also has a set of symbols which can be measured at the output of this channel. And so, having such a scenario, we also associate some probability distribution to the input symbols, because with these symbols, the sender encodes their messages, and this probability distribution will correspond to the frequencies with which the sender uses each of the symbols in the encoding of their messages. And when they send some symbol, then the action of the channel itself is modeled by a conditional probability, which just specifies what's the probability that the receiver will receive symbol Y if the sender sent X. And this distribution is used to model, for example, noise in a given channel, because, well, if it were perfect and what the sender sent was perfectly received at the other end, then this probability would just be some delta. But whenever something can happen to the symbol which is sent and it can be changed in a way, then this will be represented by such a set of conditional probability distributions. And then if we have the input probability distribution and the conditional probability distribution of the channel, we might also compute the output probability distribution at the receiver end. And one is able now to cite some key results from information theory, which say that, first of all, in such a scenario where we fix those symbols, fix the input distribution, then the maximal information rate measured in the number of bits which are sent and perfectly decoded in one use of the channel, this information rate is bounded by the so-called mutual information I, which is computed by those H functions which signify so-called Shannon entropies and are computed on respective probability distributions. And now there is 1 degree of freedom left over which this information rate may be optimized, and it is the input probability distribution. So the sender may choose to somehow optimize over this input probability or frequencies of sending particular symbols in such a way that the mutual information between X and Y is maximized. And the result of this optimization is the so-called channel capacity. So this is the ultimate bound for the information rate in a given channel. But now this whole picture may be viewed as somewhat classical because there is a way to go quantum and to generalize it. And we make this by the following observation. And it is that each actual communication act is always performed by using physical objects and sending them through some physical media, and also at the end performing some physical measurement on it. Therefore, a more general picture would be to say that the sender has at their disposal not some general symbols, but some quantum states. Then these states are sent through a channel, which is described by some map lambda, which transforms the input states into output states. And then at the other end, the receiver is free to perform any measurement they might want to perform on the output states in order to receive as much information from them as possible. And the measurement outcomes of this measurement will be denoted by the variable y. And now in this picture, one is able to cite some analogous results. First of all, the mutual information, when optimized over all possible measurements of the receiver, is bounded by the so-called Holevo quantity chi. This quantity is computed using those S functions, which are counterparts of the Shannon entropy. They are the von Neumann entropy calculated on quantum states. And I should also note that rho bar is an average input state sent by the sender. What's important to note is that this optimization is not constructive. So the Holevo theorem gives us the tight bound on mutual information, which results from optimization over all measurements, but it does not give us the concrete measurements which are optimal when it comes to maximizing information transmission. And also one can now optimize this over the input ensemble, but importantly now, not only on the input probability distribution, but also on the set of input quantum states over any states we might want. And when one does so, one recovers the so-called classical capacity of a channel. So this classical capacity is the ultimate bound on information transmission in a given channel, which is allowed by quantum physics. Therefore, maybe the name classical is a bit funny, but it just means that we are still talking about transmitting classical information, so bits through such a channel. But now, an important observation to make is that if one actually chooses some concrete set of input states and also some concrete measurement at the other end, then we practically go back to the classical picture. Because then we can just label our states by some symbols, x1, x2, x3, and so on. We have our measurement outcomes, knowing the measurement, and also the conditional probability may be just calculated using the Born rule. So in this way, when we fix the set of states and we fix the measurement, we will be able to calculate the capacity in the classical picture. But this capacity in this concrete scenario will always be limited by this quantum mechanical bound of classical capacity. But if it so happens that doing so, we get capacity which is equal to the classical capacity, then we will be able to say that great, we have found the optimal states to use and the optimal measurement to perform. But well, it's not always like that, unfortunately. So now I will slowly converge to my actual topic, which is a lossy photon channel. And this is a particular communication channel which we consider, through which one is able to transmit quantum states of light, general, composed of photons. And this channel is characterized by some transmission coefficient eta, which gives the probability that each single photon will make it across the channel. So in other words, with probability 1 minus eta, each of these photons can be lost along the way. So this channel, I guess, is quite intuitive in a way that it just corresponds to sending photons through some media which can absorb them stochastically. Now, it's important to also give some constraint on the input distribution. And a reasonable one is to constrain the input energy, or in other words, the input average number of photons which the sender of information uses. If one didn't do so and allowed the energy to be unbounded, well then, generally the capacity could also be infinite. But this is a reasonable assumption that we make. And now when it comes to this particular channel, it turns out that the classical capacity of it, this ultimate bound, is known. And it is given by the following formula. And now I would like to make two observations. So first of all, what if we make this lossy channel, well, not lossy, that is, we fix the transmission to be 1. So we will have a perfect optical channel. Now, then it turns out that there are actually two ensembles of quantum states with which one is able to attain this classical capacity. So first of these ensembles is a Fock state ensemble. So we will say that the receiver, if they use Fock states and send them with probabilities given by this geometric distribution, then classical capacity can be achieved. And a second ensemble is an ensemble of coherent states, where now the sender uses coherent states and sends them with such a probability density function, which is Gaussian. And the main difference between them is that the alphabet of Fock states is discrete, because we have 0, 1, 2, and so on, photons, whereas the alphabet of coherent states is continuous, because the alpha parameter can be, well, is continuous. And now, why do I say that with these ensembles we are able to attain classical capacity? Well, this is observed via the observation of the whole-level quantity. So if the channel is perfect, actually, if we send pure states through such a channel, then those pure states arrive undisturbed at the other end. Therefore, the output states are pure. And in the whole-level quantity, the second term actually consists of entropies calculated on the output states. Well, the map lambda is identity in this perfect scenario. And as we know, the entropy of pure states is 0. Therefore, this second contribution cancels out, and we are left only with the entropy of the average state. And in both of these two cases, the average state is the same, and it's the thermal state of light. And now, if one calculates the entropy of this thermal state to recover the whole-level quantity, one actually recovers precisely the formula which I cite here. So we recover the result that the whole-level quantity is equal to the classical capacity. So what this tells us is that, well, in theory, with those ensembles, it is possible to, well, think of some communication protocol in which the capacity will be equal to this bound of the classical capacity.
Karol, may I stop you?
Yes, sure.
Yes, because you didn't introduce the lossy channel in a physical sense. So I understand it's a beam splitter with a vacuum put in another port, no? So
exactly.
Maybe
yes,
for the other listeners, if I put a thermal state in the other port, this would break kind of your analysis, no?
Yes, exactly. We assume such a model of this channel.
Okay, thanks.
And also one other comment, because the statement that this output state is pure is only true for coherent states, yes? Not for Fock states.
But with perfect transmission, I would say that for Fock states is
for
also
perfect.
true.
Okay, I thought
yes.
you are describing losses as well. Okay, good,
I will come to this in a moment, but now I'm talking about the perfect scenario. So yes, we have whole-level quantity equal to the classical capacity, but this does not mean that we know of an optimal measurement to use, because as I said, whole-level quantity is optimized, is the result of optimization over measurements. But in the case of Fock states, we know of such an optimal measurement, as information in them is encoded only in the number of photons. So a photon number resolving detection or direct detection will be optimal, because it will extract full information from them. So in this case, when we assume this ensemble of states and this measurement and calculate the capacity in this scenario, then it will be equal to the classical capacity, and well, we have found the optimal way to communicate. Unfortunately, for the coherent case, we do not know of an optimal measurement, so we only say that in principle it should be possible that such a measurement should exist, but we are not sure what it is. And now the second case is when we actually introduce losses. So it turns out that for coherent states, they still are pure at the, well, after propagation through a lossy channel, they still arrive pure at the other end. Only the amplitude of them is damped by a factor of square root of the transmission, but still they are pure, and therefore the same argument with the cancellation of the second term in the whole level quantity applies, and we are still able to attain classical capacity, but also still do not know of an optimal measurement to use. Now, unfortunately for the Fock state case, this is no longer so, because now when there are losses in the channel, then the states which arrive at the output are mixed, and they are a mixture according to the binomial probability distribution, which can be just interpreted as the probability of some L number of successes when the success is the successful transmission of a photon, of which there is the eta probability. And now, well, this means that the second term in the whole level quantity does not cancel out anymore. We do not attain classical capacity, but still the photon number resolving measurement will be optimal because still information can be encoded only in the number of photons. Now, I should also make, well, an important reference to which we will compare our further results, and that is to say that, all right, we do not know of an optimal measurement for the coherent states, but we are free to choose some. We can set some specific measurements and see under this constraint what is the capacity attainable with those measurements. And such two, well, classical measurements are the homodyne or quadrature detection. So homodyne detection, which measures 1 quadrature of light, and also heterodyne detection, which measures 2 orthogonal quadratures. But at the cost of more noise. And now, well, one is able to compute capacities with these measurements using the so-called Shannon-Hartley theorem, and one, well, arrives at such expressions. And what one is able to see that those measurement schemes are not that bad in the limit of very large, well, signal energies or maybe output numbers of photons. Especially the homodyne detection achieves about a half of the classical capacity, which I also draw here, whereas the heterodyne detection actually has asymptotics the same as the classical capacity, but there is always a finite difference here in the value of 1 nut of information, nut being, I believe, logarithm base 2 of e bits. And in the opposite regime of very low signal powers, well, those measurements are basically not that good. Homodyne is twice as good as heterodyne, but they do not come close to the classical capacity. So I talk about those cases because, well, they can be thought of as kind of like state-of-the-art techniques of measuring of communication through such a channel. And to these, I will also compare our further results. So now a brief summary of what I said. Again, for perfect transmission, both the Fock ensemble and the coherent state ensemble are able to attain classical capacity. If we, however, introduce losses, then coherent states still attain classical capacity, whereas the Fock state ensemble does not, and we actually do not know what capacity is then attainable by them. But on the other hand, we know of an optimal measurement for the Fock state ensemble, which is always PNR, but we do not know of an optimal measurement for the coherent states. Actually, if we fix the PNR measurement for Fock states, then, as I noted previously, the conditional probability of the channel of measuring L photons where K, the K state was sent, is a binomial distribution. So this is an interesting fact in our opinion, that Fock states attain classical capacity for perfect transmission, but only when you introduce even a minimal amount of losses. This is no longer so. And still, we always know of the optimal measurement to perform while communicating with them. Therefore, we chose as our first task to, well, find this Fock state capacity in the general case and see how does it compare to capacities attainable with coherent states, for example, such as the quadrature detection method capacities which I talked about previously. So this is the first thing. But then we also chose to think about what actually is the capacity attainable with a coherent state ensemble, but if we restrict ourselves still to direct detection at the output, so to counting photons. And actually, if one does so, then one recovers a very well-known case in information theory, which is the so-called discrete time Poisson channel. So now the statistics are of, well, counting L photons where state alpha was sent are given by a Poissonian distribution. And this actually defines the discrete time Poisson channel. And it has been extensively studied. Well, first of all, maybe because the capacity of this channel is still unknown, which is surprising since the formulation of it is not that, well, complicated, quite simple. And second of all, these statistics are just obtainable when we measure classical light using direct detection. So knowing the capacity of such a channel would be helpful. And therefore, we also chose to focus on this case and to maybe see if we can say something about the capacity of this channel, which again is realized also in the picture of using coherent states with a PNR detection at the output. So what is known about this stuff up to now? Well, basically the asymptotics. So if we consider the large output numbers of photons, large output energies, then it turns out that actually both the Fock state ensemble and the coherent state ensemble under PNR detection attain approximately half of the classical capacity. So just as the Homodyne detection one. And in the opposite regime, it actually turns out that, well, if the output numbers of photons are very low, then both of these ensembles asymptotically behave like the classical capacity bound. And well, the question remains to actually what happens in between those two regimes. So in order to answer this question first for the Fock states, one could try to calculate this capacity analytically, which would entail optimization over the input probability distribution, well, in principle, infinite. And this basically turns out to be quite a formidable task, which doesn't lend itself to easy analytical treatment. However, there exists a quite interesting numerical algorithm, which I will now briefly summarize, which actually allows one to numerically calculate capacities of so-called memoryless discrete channels. So memoryless, we are not talking about any memory here, and the discrete in the sense that both the input ensemble and the output set of symbols are discrete. And what's important is that this algorithm is convergent. That is, in each iteration, it will give an approximation of the capacity, and this approximation will converge to the true value in a convergent manner, and the error actually will diminish as 1 over the number of iterations. So I would briefly sketch how it works. So first of all, one rewrites the expression for mutual information in a channel in such a form which is equivalent to one I cited previously. And the second term, this conditional probability, one also, one would normally have such a term there, but one can replace it using Bayes' rule with a different one. Then in the second step, we actually generalize this function, this conditional entropy, to some function j, where we replace the argument of the logarithm with some arbitrary stochastic matrix element. A stochastic matrix is just some matrix with non-negative entries, which sum up to 1 in each of the columns. So this is a generalization, but now we actually notice that one can prove that this function j attains values which are strictly greater or equal than the conditional entropy, and the equality holds whenever this stochastic matrix element actually reproduces the thing that was here previously. So this reproduces the conditional entropy. So one might think that, well, this is a bit weird that we now first generalize this entropy and then say that actually the minimum of this function is attained in the first case. But what one can view it as is an introduction of a new variable into this problem, which is this matrix phi. And now actually the capacity itself may be viewed as a kind of alternating optimization, where we first optimize over the matrices phi, and of this more general expression, this returns to the mutual information, which is then optimized over the input probability vector, but in such a way that this phi matrix element is kept constant. So this is can be intuitively thought like changing a optimization over one parameter to a subsequent or alternating optimization over two parameters. And this trick is actually pretty cool because, first of all, this optimization is convex. So doing these steps, one slowly or maybe actually quite quickly converges to the true value of the capacity. And also those steps of optimizing over phi and the input vector now can be quite simply done using, for example, Lagrange multipliers. And this method also allows to incorporate some constraints on the input distribution that we might want, such as the constraint on the input energy.
Can I ask you something, Karol?
Yes.
So, but in the second step, when you maximize over Px, then you still have this conditional distribution Py conditioned on X in J.
Yes, but well, you know that this stochastic matrix should, well, you keep this term constant in this optimization over Px, and
Yes.
well, yes, you still have this, but if I recall correctly, then basically the problem is easier if you forget about this argument of the logarithm in this optimization. So this allows you to do this optimization analytically.
So it is like that. That first step you assume this stochastic matrix to be something. Yeah, I mean, okay. In the first step you assume the probability Px, then you optimize over this stochastic matrix. Then you take this optimal stochastic matrix that you got in this previous step, then optimize over Px, and then once again optimize over stochastic matrix with this previous Px, and then you alternate those steps until you converge to the maximum. So this is how it works.
Yeah, I understand, but I just wonder, because I see that there are Px variables, there are phi, but there is also this conditional Py conditioned on X, and I wonder when.
But this is given. This is fixed by your channel. This you know.
Ah, okay, good. Yeah, sure. Okay, this is fixed. Sure.
All right.
No, now it's okay.
So this algorithm is actually quite useful, and it will allow us to calculate the capacity for the Fock state case. But note that we require the channel to be discrete. So this practically means that we cannot really use this algorithm for the coherent states case, because then the input alphabet is continuous. And well, there are some heuristic methods which kind of allow one to generalize this algorithm to the continuous case, but then they unfortunately do not guarantee convergence. Nevertheless, we will use them and see what we get. So if one performs this optimization with the Blahu-Tarimoto algorithm, one calculates the capacity for the Fock state case in the general scenario of any transmission we want. So here I draw, first of all, the classical capacity denoted here as the capacity for Fock states with perfect transmission, because then they are equal, and also those capacities attainable with coherent states and quadrature detection, which are here for comparison. So now if one lowers actually the transmission and calculates the capacity for Fock states, one gets, we think, a surprising result. So indeed, in this very low energies regime, we get what was surmised, that capacity for Fock states is very similar to the classical capacity. However, in fact, this closeness of those two holds for quite a large regime. So up to like 70 or 80 output photons, we are still quite close to the classical capacity, and importantly, we are higher than the best capacity attainable with quadrature detection. If we make the transmission a bit worse, then things still do not look too bad, because we are still quite close to the classical capacity and only get worse than heterodyne detection around 10 output photons. well, if one makes the transmission even worse, then things get not that good anymore. But what this observation allows us to say is that surprisingly, Fock states offer information rates which are quite noticeably higher than quadrature detection and not that far from classical capacity, also in the regime of the small or moderate output number of photons, if the transmission is relatively high. So this suggests that basically Fock states could become relevant in communication over scenarios where you have high transmission, so for example, short distances. And you also do not use high, very, very high Fock states. You have not a large number of photons. An example of such an application could be, for example, optical interconnects, which are interfaces into which you transmit information on short distances, but not as usually with electrical signals, but with light. So this suggests that, especially given recent progress in production of PNR detectors and also the production of low Fock states, that they could become relevant in such scenarios. And now I will switch to talking about coherent states under PNR detection at the output, so the discrete time Poisson channel. So first of all, let me show you the best bounds on this capacity which are known. So this is the best lower bound. This is actually achieved by just setting at the input a specific distribution, which is a gamma density function. And then one attains mutual information given by such a curve. This is the best lower bound, analytical one. And this here is the best known upper bound to this day of this channel. So we see that there is still some gap between them. And well, we used one of those heuristic generalizations of the Blachout-Arimoto algorithm to compute also, actually using them, we are able to compute lower bounds on the Poisson channel capacity, so with coherent states and PNR. And we arrive at such results, which are, well, right in between those two curves, which first of all prove that this bound, this lower bound, is not tight. And second of all, suggest that there still might be a bit of room for improvement of the upper bound. And I will actually come back to this later. But now, actually, let me say that as a byproduct of the Blachout-Arimoto optimization, well, this optimization basically updates in every iteration the input distribution to arrive at the capacity. So it also calculates the optimal input probability distributions in a channel. So for our Fock state case, I will now show some characteristics of these optimal input distributions. And well, first of all, what one is able to see if one lowers transmission from the perfect one is that it significantly raises the probability of sending 0 photons in a channel. So this is the optimal probability which should be used in a channel. And this basically can be intuitively explained as the fact that actually sending 0 photons is like the only act of communication in which you are certain that the receiver receives exactly what you sent. That is, if you send no photons and also assume no noise, additive noise, then the receiver, in only this case, is sure about that you sent 0 photons. And therefore, this is not strict, but this may be an intuition which suggests why this is so. But what's interesting is if one actually looks at the tails of those optimal distributions for the very low transmission case, because then we see that those tails exhibit some local minima. In here, I plot probabilities from the Fock state number 1, because the probability of sending 0 is well, much higher than everything else. And in fact, if one looks at the lowest transmission in this upper plot here, there's only one such maximum here. And this actually suggests that while communicating through this channel in the regime of very high losses, so very low transmission, what becomes optimal to use is a kind of an on-off keying strategy, which basically means that you either send 0 photons or you send some very high number of photons. So the fact that there is only one such local maximum here is a hint as to the optimal communication protocol one should actually in use while communicating through such a channel. And also looking at this, one might notice that these distributions are not functions of the product of the transmission and the average number of photons, eta and bar. This is just seen because those two cases, actually the colors correspond to the same product, and those distributions are very different. Therefore, this just proves that the optimal distributions are complicated functions of both the eta parameter, so the transmission, and both the average number of photons. But these are some observations as to the optimal probability distributions. And another observation that we make is that, all right, those distributions are not easily explained analytically, but actually we propose that if the sender uses a negative binomial distribution of Fock states at the input, which is a distribution defined in here, and this parameter R is a free parameter, non-negative one, over which one can optimize the mutual information. And if one does so, it turns out that the mutual information obtainable with such an input distribution is very close to the true capacity calculated with the Blahu-Tarimoto algorithm for transmissions approximately greater than 10%. So on this plot, it may be seen because, well, the dotted lines are the rates obtainable with such an input distribution, and the solid lines are the result of the optimization with this Blahu-Tarimoto algorithm, and they practically coincide for transmissions higher than 1/2, and are not too far for transmissions even slightly lower than that. Now, as I promised, so actually this is a discussion of the Fock state case, but as I promised, we also wanted to say something about the coherent states with PNR detection at the output, which is the discrete time Poisson channel. If one plots the quotient of the Fock state capacity over the coherent state capacity calculated with those heuristic methods, one actually notices something interesting, and this is the fact that this quotient is actually never less than 1. So this value of 1 seems to be some lower bound on it. And actually, this can be rigorously explained using a data processing inequality, because one can see that actually the statistics of using coherent states and measuring the number of photons at the output can be obtained as a statistical mixture, actually a Poissonian mixture of statistics obtainable with Fock states. So in here, this PLK is the conditional probability of measuring L photons where the Fock state K was sent. And if one mixes them with the Poisson distribution in such a way, one obtains the conditional probability for coherent states. In other words, one can always perform some communication scenario with Fock states and then mix stochastically your results in such a way that it looks as if you were communicating with coherent states. Therefore, this mixing is a form of post-processing, and the data processing inequality basically says that with post-processing of your information, you cannot increase information. So from this, we know that actually, when we switch to coherent states, we are never able to get a capacity higher than with Fock states. But we take this observation a bit further, and we actually prove that the Fock state capacity approaches exactly the discrete time Poisson channel capacity in the limit of the transmission going to 0, while keeping the output number of photons constant. So in here, I plot these lines of a constant output number of photons. And in fact, if one goes along those lines with lowering transmission, one approaches this limit of 1 of those two capacities being equal to each other. And the argument which explains that basically relies on the fact that the binomial distribution, when taken in the limit of transmission going to 0 and the number of photons going to infinity, but in such a way that their product remains constant, this distribution approaches the Poisson distribution. So when we are in this limit, if you are communicating with Fock states, it looks as if you were communicating with coherent states. And also remember that with Fock states, you can never get anything lower than with coherent states. And therefore, basically in this regime, those capacities are equal. And what this allows to say, this first of all allows us to give a method of computing the discrete time Poisson channel by just computing the Fock state capacity in this particular limit. And this will yield the capacity of the Poisson channel. But this will also, and this can be done, for example, with Blahu-Tarimoto in a convergent way, but this will also give you the optimal input distributions, and they will be the same both for the Fock state ensemble and the coherent state ensemble. And not only that, but this fact also proves that, well, if you can get the optimal input distributions for the Poisson channel by considering the Fock state case in this limit, and the Fock state alphabet is discrete, then this also proves that the optimal input distributions for the Poisson channel are also discrete. So the alphabet is continuous, but it turns out that the optimal thing to do is actually pick some discrete alphabet from this continuous set. And this is a fact that actually was proven recently by a quite complicated mathematical argument, and we provide here more justification of this fact. So to conclude, first of all, we have calculated the Fock state ensemble capacity for the lossy photon channel. And we note that in the regime of a low number of photons at the output and also low losses, this capacity is noticeably higher than information rates achievable with coherent states, either with coherent states and PNR detection or coherent states and quadrature detection. And it also comes quite close to the classical capacity bound. And this results in this notion that given the progress in PNR detectors and production of Fock states, well, using them might become relevant in such communication scenarios, predominantly over short distances with high transmission. And when it comes to the conclusions for the Poisson channel, we showed that the capacity of this channel is equal to the one obtained for Fock states in the limit of small transmission and keeping the output number of photons constant. And this allows not only to compute this capacity, but also identifies the optimal probability distributions for this case, which are and also the optimal amplitudes for the coherent state alphabet. So for some further details, I invite you to check out our archive. And now I would like to thank you for your attention.
Thank you very much, Karol. I will clap for everyone. So are there any questions from the floor? Let me maybe unmute. Yes.
I
Claudia.
actually have one question. Sorry for the background noise. Is the noise, like in communication channel, the additive noise is practically the dominating one or not necessarily? And because I want to put it in perspective, and is the transmission coefficients, what kind of transmission coefficients you can get in practice, like for optical states?
Mm-hmm. So this whole analysis of ours was performed in the only pure lossy case. So we did not assume any additive noise here. And this is actually a next step which we intend to do to see how these numbers and conclusion change when actually one accounts for additive noise. So this remains to see, I guess. And actually for the values of such transmissions, then I'm not too sure actually. So I think one more in touch with experimental realizations should be more able to say whether such transmissions are achievable today.
Well, maybe one observation.
Maybe I can comment on this.
Okay. Yes, please, Marcin.
So, I mean, regarding this transmission, it all depends on the kind of communication you consider, because, well, if you consider communication on very long distances, then the transmission will always be very low. But, well, for example, in those optical interconnects, then the distance is really, really small. So I guess such, like, eta equal to 90% or 95% should be doable.
But you mean in a free space or in a waveguide, or like, does it depend really, or you get similar transmissions through the free space and through this?
Well, in a free space, if you have short distance, then your beam almost, your beam does not diverge. So, well, basically only. So basically, if your distance is very small, then you'll have very high transmission. And through waveguide, it also should be very similar if you take a good waveguide, I think.
Well, maybe the general comment, which is
can I have a comment on this?
Okay, everyone will have a comment, but maybe I'll stop and ask for other questions, because before we comment on it.
So I can turn my comment into a question.
Then that's perfect. Then the floor is yours.
Okay. So if I understand correctly, I think it was eta, yeah, the loss for the channel that you have shown in the graph where you show beating the coherence state and heterodyne homodyne detection. This also includes the loss of the detector. Yes. So now achieving like 90-something%, yeah, it has been done experimentally, but using like dilution refrigerators and millikelvin temperatures. And the question is, would there still be an advantage with something that would be more experimentally realistic? Let's say 80% detection efficiency. Let's assume that the transmission is 80%, yeah, where most of the loss comes from the detection efficiency, and so-called pseudo photon number resolved detection, like with an array of detectors and beam splitters.
Well, then for sure things would be a bit worse.
Yeah, but would they be terribly worse, or would still there be a advantage?
So if it was 80%, I do not think it would be much worse. It should still be around. It should still be advantages in the low number of photons per channel use case. But well, in a practical realization, one probably should also, because for example here we assume this perfect photon number resolving detection methods, and well, an analysis of what imperfect here does, so some noise at the other end, we have also not included here, and
okay,
it would probably limit the capacity, but it's hard for me to say how much.
Okay, well, that's an interesting question for the future then. Okay, thank you.
Thanks, Michał. So are there any more questions?
Maybe I can ask something simple.
Yes, please.
So just to make sure that my intuition is correct, this asymptotic fact that using Fock states we get 1/2 of the optimal capacity, you can intuitively just say that it's okay. It's something like you in heterodyne detection, you measure both quadratures, so you get 1/2 basically if you just focus on one. So it's like with Fock states you just have access to like amplitude and not the phase. Yes. So you can say that this 1/2 is due to this. Yes.
That's how I understand it too. Yes.
Excuse me, are there any analogies with single electron transport? Photons are having different statistics of behavior, but can you find some analogies with single electron devices?
I'm not sure. I haven't thought of this.
Okay, because like beam splitter can be, you know, the fork of quantum dots, right? So in a sense, one can find analogical kind of behavior, but obviously this analogy will not be fully transformed, right? So it's just a kind of open question, since, you know.
I mean, maybe from me, we're talking here about bosonic channels. So
yeah.
So I mean, this is all theory of bosons. So going to fermions, it's a different story.
All right.
Okay, then I have a last question, and maybe I close it then. I have a question, maybe more technical, because you said at the end, this was your last point, that your analysis allow you to now know how to design the optimal encoding for coherent states, no? This is some kind of, you said that.
Well, they allow to arrive at the optimal distributions.
Mm-hmm.
So this could be, well, thought of as the optimal encoding, but as it's usual in the information theory or mathematics, you do not know specifically what such an optimal protocol would be. You only know the input, the optimal frequencies with which you should use your signals, but not the actual way with which you should do so.
Yes, but then, because you said it is the optimal, but you just proved that there exists one, there could be other ones that are also optimal that don't rely on discretization. This is my question. So
yeah, I thought about it.
Or is it the only one? Is it if and only if, or it's just some kind of?
I thought about it, and I think I'm not sure, but I think this kind of like equalization will the ability to think about it as the Fock state ensemble case, and the fact that Fock states cannot be worse than coherent states in this limit. I would surmise that this correspondence is one-to-one, is perfect. So this would give the optimal distributions, but I'm not 100% sure. I mean, from this analysis that those guys did, it seems that it is always the case that the optimal distribution for coherent states is in fact discrete. But yeah, so on this we agree with them. But I'm not 100% sure whether the distributions that we would arrive at are the only
discrete ones that
ones.
are optimal.
Mm-hmm.
Okay, thank you. So if there are no more questions, I think there are not. Let me thank Karol once more, and let me close the session. Thank you, Karol.